Okay, hello guys. How's the course going? I hope you're having fun. So I think the way we will do this is, as usual, you guys can start typing your questions and we can answer.
Yeah, it's speaker.
Okay, so let's start with the first question of today. Lokesh asks how to know the starting and ending point of a root locus branch. I think the first step of the construction, what we teach is about the starting and ending point, right? So we want to investigate how the poles move as the gain k increases from 0 to infinity. Right? You could also have had questions of minus k, but it's the same thing. For k equal to 0, it was, I think, it's kind of explained that when k equal to 0, you start at the poles, and as k goes to infinity, you end up at the zeros which are available. And if there are if there are less number of zeros as the poles, the remaining poles will go to infinity. I think it's a very straightforward procedure, which is on one of the very earlier slides on the root locus. If that doesn't help, then Lokesh, get back to us. We'll try to answer your question. But how to know the starting point? Starting point is the poles, and the ending point are the zeros or the zeros at infinity. That's all I could say at the moment. Okay, so there is a question from Amol, and the question says, why we do steady-state analysis in a frequency response? I think we do steady-state analysis in both cases, right? Not in time response and also in frequency response. So if you look at how the derivation goes, if you do the partial fraction expansion while we do the frequency analysis, I think after all the transients die out, what is left is some kind of a sinusoidal component, such that if the input to a linear system is a sine wave, the output is also a sine wave. And what changes, or what could change, is just the magnitude of the input signal. So this, I think, the derivation is clear, right? And then what we are then looking at is only the frequency response will just be on what is actually the steady state response. So the magnitude might change, and the phase, there might be some kind of a phase shift depending on what is sitting inside the transfer function. So I think that's the reason, right, why we do the steady state analysis. I think again the partial fraction expansion will actually tell you a little more on that. So whatever is remaining at steady state is only the frequency component. All the others would actually die down because of the transients. Okay, so there were several questions also on the forum after the breakaway point. Which branch goes to which side? Okay, so question number one, or the point number one here is that, okay, nobody really moves, right? So take a particular value of k, that will give you some locations. Change the value of k, that will give you some other locations of the poles. So it just pictorially we say that as k goes from 0 to infinity, and the open loop poles or the closed loop poles moves from the open loop poles to the zeros, right? So all those points on the graph will just tell you the locations of poles for that particular value of k. So it's not really important to see which branch goes with side. It doesn't even go, right? Nobody goes anywhere. It's just that the graph, if you look at all k starting from 0 to infinity, it just looks as if the poles are moving in a smooth. There are breakaway points in that way. So nobody moves anywhere, right? It doesn't really matter if at the breakaway point this guy is going up or it is behaving that way. It doesn't really matter. So there is a question which is kind of interesting. Does the methods of stability and other things like root locus apply to non-causal systems too? I wouldn't say, okay, so we are restricting ourselves to causal systems so that, all the analysis which we do here are for causal systems. So the notion of root locus may not exist there. There could be some other methods which I wouldn't remember now. But for this course, or all the physical examples which we consider here are restricted to causal systems. And the non-causal analysis is possibly a subject by itself. So, well, these are not applicable, or even the notions of stability, may alter a little bit. But okay, we can skip that for the moment and restrict our discussions to causal systems. In question number 1, assignment 5. Okay, I don't remember, or I don't have the question paper with me here. So Rajesh Kumar Sahu asked this question of why is the root locus path right-sided? Why not left-sided? First, I do not know what is a right-sided root locus or a left-sided root locus, because we haven't defined anything like that. Possibly what you mean is for negative values of k. Okay, so what usually happens is I write my characteristic equation as 1 plus k times gh is 0, and then look at how the poles of the characteristic equation or the solutions of the characteristic equation change as k goes from 0 to infinity, which essentially means k times gh is 1 plus j0, right? Or if I just look at minus k, so I just look at k times gh is minus 1, or 1 with an angle of minus 180, however you choose your orientation, right? We're just comparing complex numbers and see how how the solutions to the characteristic equation evolve. If that's what you're meaning by right-sided and left-sided, this could be my answer, but I'm not really clear if any terms like this exist in any textbook or any literature of what is the right-sided root locus and the left-sided root locus. Another question by Yash, which asks, at the breakaway points on the root locus, the root sensitivity is infinite. Okay, I do not remember of defining anything like the root sensitivity. There are terms on sensitivity of a transfer function, which we just had a mention of somewhere, but I do not know what does it mean by root sensitivity, especially at the breakaway points. You may want to be a little more clear on that. Okay, so Amol, I think the question which you asked of, if we take gain value negative, what is the effect of negative gain on root locus? Well, you just again have to write down the steps in the same way. So you're looking at now g times h, or k times g times h is 1 plus j0, and you convert it into the equivalent phasor. Or when I'm looking at a negative, I'm just looking at k times gh is minus 1 plus j0. So, and then the analysis all just follows. So it's just replacing k with a minus k, and all the steps just follow as a symmetry. And then what happens at k equal to 0, k equal to then you're looking at minus infinity to 0. So what you if I just look at graphically, so say suppose your plot starts like here, k equal to 0 to infinity. So if I look at the minus infinity, something will start from minus infinity and reach this point at k equal to 0. So I'm essentially looking at minus infinity to 0. It will just be a complete picture of the entire thing from minus infinity to infinity. Those steps, if you just write down very carefully, are just very simple, very much related to what we have done. That it's just of handling that minus 1 plus j0 as one angle plus or minus 180, depending on what orientation you choose. So the effect is there for you to see, right, once you plot it. So the effect is, again, the roots will change for k equal to minus infinity till k equal to 0. The effect is then for you to plot it exactly and check for a particular system. So the effect of the positive gain is also the same, right? We're just saying what is the effect of the positive gain on a particular transfer function. So I hope this is a bit clear. There's another question by Vardhan saying, are the methods of control systems applied to transmission lines? Well, the answer is yes. It depends then also what kind of models you would use for the transmission lines. So one is when I look at the transmission line from originating from the Maxwell's equations to the telegrapher's equations, they are a set of partial differential equations, which actually comes in the theory of linear infinite dimensional systems. If I were to look at a transmission line in terms of transfer functions, one way to look at it is to model it as a pure delay, right? So you have V0, I0, and you have V1, I1 based on the length of the line. You can just model it as a pure delay. Third is that there are these approximate models, right? The T model and the pi model. So these are essentially finite dimensional approximations, which you can actually write down in terms of ordinary differential equations. So once I have the T model or the pi model, I can always have a transfer function, and then all the control theory which you learn here is directly applicable to that. So the answer is yes, but then what methods depend on how you model your transmission line as an infinite dimensional system, a system with a delay, or a finite dimensional approximation in terms of the T model or the pi model. So Amol has a question: why we take omega 0 to infinity in polar plot? Okay, the way the polar plot is defined is we are looking at how the system varies as we change the frequency from 0 to infinity. So we are just looking at the system behavior for several frequencies, starting from frequency to 0 till frequency going to infinity. And that's as simple as that. We are not taking that, but we would like to see how the system responds to different frequencies, and then how the magnitude and the phase of the response changes and so on as omega goes from 0 to infinity. It's not why we take, we just want to observe that behavior, and that behavior we term it as the polar plot. There's a question by Shubham. He says, why do we mostly use impulse response, not unit step or any other response? It's not that we mostly use impulse response, right? The impulse response naturally, it is called the natural response of the system, right? I think this question was asked even even last time. So impulse response is how will your system respond to some very small perturbations. And if the impulse response is stable, you say that the system is stable. If I want to check how the system responds to some sudden change in input which stays on forever, I use the unit step input. If I if I were to look at some other responses, I think there is no mostly using the impulse responses depending on what information I want from the system. I use an appropriate test signal. So there's a thing on resonant peak of closed loop system. Okay, what about that? It's just there. It's a well-defined quantity, right? So I don't know what the question means. Okay, so the next question by Lokesh says, how do we know that the roots are on the root locus? Okay, so dk by ds might give you several solutions. How do you know if any point is on the root locus or not? Is that it should one satisfy the magnitude criterion and second satisfy the angle criterion, right? So I think it's a kind of easy test, right? How do you check if any point is on the root locus? Check for the magnitude to be 1 and then the angle criterion. And it's as simple as that. There's a question by Amol stating, what is the PID design? Does it physical modeling and not a mathematical modeling? Well, I'm afraid I think you may have to rewrite your question in a way. So there are 3 different parts of your question. One is the PID design, one is the physical modeling, and third is the mathematical modeling. You may want to connect all of this to make a unified question. At the moment, I'm sorry, I don't get what you're trying to ask. Does this make any?
Okay, I think he's asking whether we just do it as a mathematical thing or does it involve physical realization? Or can anything which is PID design can be realized physically?
Okay, so Amol, if I understand you correctly, I mean, can the design of PID be realized properly? I think so when we do lead-lag compensators, which are approximations of PID controllers, you can see how they could be realized just with passive components of resistors and capacitors. So Vardhan wants to know about non-causal systems. Okay, so Vardhan, I think if you post it on the forum, I will be able to suggest you something about non-causal systems. Maybe some very basic paper which you may want to read sometime. So just please post it in the forum, and I think whether me or Chandra will post some reference material for you on handling non-causal systems. But this would mostly be, I think, non-physical systems, because all physical systems which are governed by the laws we learned in textbooks are essentially causal systems. So Amol Patil asks, can I say PID modeling is a physical modeling? Well, I think PID realizations can be realized with ideal physical elements. Like an integrator can be modeled through an inductor, for example. Right? So similarly with the derivative component, which could in one way be modeled as a capacitor, for example. So all these are, I would say, possibly you could even do an integrator with some nice combinations of capacitive elements. So PID elements are also physically realizable elements. So when you will look at the lead-lag compensator in the frequency domain or in the time domain, I think the realizations will be discussed over there. Minimum phase transfer functions would mean, okay, so there will be one complete module on why, what is the importance of minimum phase transfer functions, what happens when we do a non-minimum phase realizations. I think just please hold on until we go to module number 10. And that is a comprehensive review of minimum phase, non-minimum phase zeros. How are these systems, what kind of systems are physically representing non-minimum phase behavior, and what does it mean by experimental determination of a minimum phase transfer function and so on. So I just would like you to hold on a bit till module 10 and then we can take up those questions. Vardhan Saxena says assignments in the schools are almost similar to the assignment given last time, so the answers to some assignment questions are open. Okay, what does that mean?
Versus questions like in the last semester we gave, like they're kind of similar.
Well, okay, yeah, I think the questions could be similar, but I think so. We believe that you will try to answer yourselves, or I mean, even if you are taking help from somewhere to answer the questions, you are understanding the process, not just blindly copying some numbers from somewhere, right? I think the entire idea is that even there are several hints available online, that you take those hints, but at the end you must be able to understand what is going on in the course. So that is the objective of the course, not really to really trouble you with questions which are seen nowhere, and you're breaking your heads to do that. Whatever you do, it's just a learning process, and if that learning process helps you, if the learning process is via some hints which helps you solve some problems, that I think is perfectly okay with me. Okay, what is the significance of the frequency domain analysis and the time domain analysis? Well, I think each one has their own kind of importance, right? Depending on what kind of responses are you expecting from the system. I think this is the entire objective of the course is also to deal with this separately over a series of lectures in time domain, series of lectures. In the frequency domain, there are few things which we could do in the frequency domain which we cannot in the time domain. For example, I could do experimental determination of the transfer function via the frequency domain. Time domain will give me how to analyze with various test signals and so on. I think if you just do the entire course and then just make down notes, I think this significance would be kind of obvious. Keep some session on MATLAB interfacing to hardware. Okay, I will think of that. Can you do some Lego experiments that has some MATLAB interface?
Yeah, but they still need some. I think they might be expecting something like.
Okay, so
Raspberry Pi kind of.
Okay, so Amol, so when you say keep some session on MATLAB interfacing to hardware, I think we can demonstrate to you some experiments on some Lego kits which we have in our labs.
Yeah,
and okay, so Jaydev says there are some links available to this which you can post, and which he can post online, and you could go through those links. I can keep a session, but it'll just be like you're watching some YouTube video, right? So I can just explain you a few things, the code and the interface and so on. If you really want, there is a general interest in the group, we can actually do that. Okay. What are the practical examples of non-causal systems? I think in the lectures I actually talked about few examples from economics, or for example, preparing for exam is a non-causal system because you are keeping in mind future inputs and then preparing accordingly. Right? The questions which appear in the exam are the inputs there. You anticipate that the question paper would be so and so, and then you prepare accordingly. So I think most of the non-causal systems are non-physical systems. So therefore, weather forecasting or any of these things which require some things, when you say, okay, based on tomorrow, what I will do today is what is a non-causal system, and there are several things which you do in your day-to-day life, right? So, for example, you go to Western Europe. So, based on tomorrow's weather, you decide what clothes to wear, like a day in advance, right? So, there are several of these real-life scenarios which are actually non-causal behaviors. But I can post some literature on non-causal systems, right, for people who are interested. Rajesh Kumar Sahu says inductor and capacitor both are linear elements, but combination becomes non-linear. Okay, so first, inductor and capacitors are not naturally linear elements, the range of operation which we are interested in, we model them as linear systems. But if I have a linear capacitor, a linear inductor, whatever combination, it will always be linear. I would really like to know a scenario where it actually becomes non-linear. I would be actually interested in looking at that, even though I don't believe that it could become non-linear. But I would really like to see, how you achieve that thing. K. Sandeep, what is 2 degrees of freedom control? Okay, so let me quickly think of an example of 2 degrees of freedom. So let's say I take this arm, right? So say there's an actuation here and there's an actuation here. This is 1 degree of freedom, this movement through the elbow joint, and one is to the shoulder, right? So these are the systems which is 2 degree of freedom, as simple as that. Lokesh asks how complex points of the root locus form a circle. Okay, I do not really understand again this question, but there could be root locus plots which end up looking like a circle, and there are several of those examples which textbook says that take a system like this, prove that the root locus is a circle. Yes, I think the effect of PD control on rise time and settling time is actually, it is explained very detailed in the slides with lots of examples also, lots of plots. I really would like you to see the opening videos or opening slides of module number 7. And these are really comprehensively explained, and I think my TA Akshit did a very good job in putting down stuff which you will not really find in textbooks. So just go through that. If something is not clear, I will be happy to answer. Okay, there is a question. Are there any physical systems whose poles are on the right of plane? Oh, absolutely. I think you take a all-pass filter, right? Which all-pass filter which has a transfer function s minus 1 plus s plus 1. That is a physical system which has poles on the right half plane. And then I'll teach some more of those right half plane. Okay, sorry. You're talking of poles of the right half plane, right? I think, yeah, of course, there are systems which are unstable naturally, whose poles are on the right half plane. So take an inverted pendulum, for example. The upward position is always unstable. So it has a transfer function 1 over s minus 1, s plus 1. So one pole at minus 1, one pole at plus 1. So it is naturally unstable, and there are several of these examples which are naturally unstable. Simple example is an inverted pendulum which has pole on a right half plane. So Lokesh, again, I think so not all complex points of a root locus will form a circle. There could be several specific examples where they could form a circle. That's all I could say. Case on the stability in the sense of Lyapunov. Well, I think Sandeep, if you could write to me separately, I can tell you something on this, because that is something which comes as a second part of a control course. So I would want you to, maybe I can write to you separately on this, but within whatever we are discussing in this course, I am not really covering this topic, and also I cannot explain you, within a couple of minutes on this live session. I can maybe use the board, but I wouldn't want to use that because there are lots of concepts to be introduced before I actually do that.
Actually, the roots are all the same.
Okay, this is interesting. Shubham asks how to apply Nyquist criteria about the origin. Would it be the same? The starting lectures on Nyquist actually have the conditions based on encirclements of the origin, and that we shift to -1 plus J0. The conditions are the same, only that when I am looking at n equal to p minus z, I will look at it about the origin. If I am shifting it to -1 plus j0, I am looking at encirclement about the point -1 plus j0. So it's just the same, right? Depending on if I'm looking at the plot of 1 plus gh or just about gh equal to -1. The condition still remains the same. And this is actually not the stability criteria. N equal to p minus z will just tell me what are the number of encirclements, right? This is just a formula for the number of encirclements, and we know why this formula comes from. So it then depends on, so this P are the number of right half planes, so right half unstable poles, and Z is what comes from the 1 plus GH, right? So this is not the stability criteria. This is just about the number of encirclements. Stability criteria depends on if there are open loop unstable poles or not. Right? If P equal to 0 for the open loop, then N should be equal to Z, and then it becomes kind of straightforward. Right? This is just about the encirclements. It is not a formula for stability. So just be careful of how to use this formula to find the conditions for stability. Time response, frequency response, state variable analysis, which is more accurate and why? Okay, these are all different methods, and each method has its own usage. And for example, if I look at state space, it is easier for me to deal with multiple input, multiple output case. And of course, a state space, when I look at a transfer function, it will not tell me about pole-zero cancellations, which we learn in module 12 on state space. There are several things because when I have the transfer function, I know that the system can be controlled, or I assume the system is controllable. So these definitions will come up a little later, but the state space analysis, if you look at the part, the analysis actually tells you a little more information of the system, which sometimes you miss in the transfer function, and will tell you what is that information that is missing in the state space in the transfer function, and why state space is a little more bigger domain of analysis. Of course, we can also have multiple input, multiple output transfer functions, but several of these things of asking yourself, is the system controllable or not, becomes much easier when I look at it from the state space point of view. What is the use of root locus and where it is practically used? I think you can wait in module 8, where we actually will use root locus to design control systems, to have control design, we'll solve control design problems using root locus. So that will be a little more clear when we are into module 8. Okay, so yeah, I think that seems it for today. If there are no more questions, if you think a different time slot is suitable, just let us know, and we will try to arrange accordingly. So possibly we could have a little more participation. If there is more questions on hardware interface, we could try and organize one live session where we can do some experiments, but that will depend on if there are more than a few people interested in doing that. So just hardly one or two, then we can point you to the appropriate links. Okay, so please feel free in posting questions in the forum, discussing in the forum, and yeah, and any suggestions are also welcome if you want a few things to be done in more detail if things are not clear. All those things are encouraged. So please make use of the forum, and then keep writing to us. Okay, thank you.